There are cross peaks which lie very near to the diagonal, and for huge diagonals we are not able to see the cross peaks which are near to them, and therefore it has an added advantage. This is basically telling you exactly how these terms come about, and in the cozy experiment and the super cozy experiment, which magnetization gives cross peak, which gives diagonal peak. Okay, and experimentally it works. This is a case where it's a two-spin system, and this is not given to you. Okay, this is a very simple diagram. I didn't make a copy for everybody for that. Which just basically tells that if we put a delay, you can get a cross peak which is bigger than the diagonal. And a real example is of a decapeptide, and this picture is with you. Okay, and this is a very quick experiment, a 20-minute cozy. 20-minute cozy with 256 data points for full 10 ppm range, and it was a surprise to me that even in 20 minutes we got fairly good number of cross peaks. They are not noise, they are not dirt from Xerox, they are real cross peaks. They are real cross peaks, even in 20 minutes. With a 23 hertz per point digital resolution. It just tells you that it's very difficult to cancel the antiphase. Very difficult to cancel this slightly shifted Lorentzians, which are antiphase. If you just slightly shift them and they're not cancelled. This was news to us. Anyway, okay, when we did a super cozy experiment, you can see exactly 20 minutes. We can still get, there's a very large increase in the cross peak intensities and a decrease in the diagonal peak intensities. In fact, this particular peak, diagonal peak, has almost completely disappeared, and the cross peak is quite strong, where there was no cross peak at this place. And in general, all the cross peaks have increased in intensity, and all the diagonal peaks have decreased in intensity. So, looks like a good experiment. Everybody should do it. The problem is that if you need also very good chemical shift resolution, then you don't need to do such a crude experiment. You need to do a better experiment to begin with. All right, we also thought how to improve the intensities in the sexy experiment, and I very quickly will go through it. Sexy is anyway dead. Anybody who's doing sexy, please pardon me. But, one can also put delays with 180-degree pulses in the spinacle correlated experiment also, and you can do it in the beginning of the T1 and T2 period, or you can do it later. As we just described it in here, it's in the beginning. And one of the disadvantages of doing that in the beginning was that the cross peaks went away into 45-degree angle rather than a 135-degree angle. There is no real disadvantage, but if you are used to looking sexy peaks in this angle, you say, I don't like this. So if you don't like it, the information content is exactly the same. But if you don't like the looks of it, you can put another 180-degree pulse. Okay, and you get back your old look. And the plus-minus character is in this sexy experiment of the cross peak has gone into the diagonal peak in the super sexy, and the cross peaks are in phase as expected. Okay, and on the same two-spin system, the result is quite dramatic because it's a long T2, and the sexy experiment in this, a crude one, gives very, very small cross peaks, but a super sexy gives fairly nice cross peaks. And so it works in principle for a dipeptide. Also it works, and mostly those people who have good digital resolution and not very and well separated chemical shifts, they find that these experiments can be used. And basically, it works in some cases, it doesn't work in many cases. The advantages, as I said, was that you increase the cross peak intensity, you can interpret it as a decrease in experimental time, if you like, or you can say I have more time, I can do signal averaging for longer time, as you like. This is basically the point. It reduces diagonal peak intensity, and that reduces the dynamic range in the experiment, in the spectrum, and allows detection of cross peaks which are near to the diagonal, and as a result it reduces T1 noise. T1 noise is not something that I didn't really talk about so far, but T1 noise is what, I don't know whether I have a spectrum which I could show you, which has the T1 noise. I mean, it's so ever present, it's difficult to get rid of the T1 noise, and it's so strange I don't have a spectrum which I can show you which has the T1 noise at the moment. Anybody has yesterday's notes with them? I can borrow it and show you the T1 noise. Oh yeah. These long ridges that run across are very annoying, come from several factors. Not all of them have been identified so far. And I think there are several sources which have been identified. One of the main reasons is that if you have a sharp line, it has not decayed fully before you cut off the signal. It gives you sync tails all along. Okay, well, we still are on the super schemes. There are disadvantages that you can lose signal during delay due to line width problems or T2 problems, and so one must know how is the optimum value of delay. You get mixed phases, and so how to clean phases. And I would like to go through that fairly quickly. The main reason to go through is because it's our work. I don't think many other people will emphasize this so much. And so the signal at this point of time, at the end of delay in T1 and the end of delay in T2, before we start detecting, and just looking at the cross peak part of it, is going to have two parts. One, which is antiphase, has a cosine dependence. I'm sorry. This is the signal I'm looking at this point of time, not at this point of time, at this point of time. And similar analysis can be carried out for this one. There's no need to do it. One can just, from the results of this, same interpretation holds good for the delta 2 delay. Okay, at this point, we have two parts. One, which is a cosine in T1, which is in phase, and a sine which is antiphase. Now if you had decoupled spectra or long range coupling where you could not have resolved, basically our total dependence of the intensity is on this term. But here we have partially resolved sine, so it depends on both these terms. And that's basically the difference between a delay cozy and which is done for long range coupling, or a super cozy which may be done even for not so long range coupling. It should be done even for normal couplings. Actually, in standard cozy algorithms nowadays that you get from vendors or machine manufacturers, a little bit of delay is very generally introduced during T1 period. Okay. So the optimum signal is a function of the value of the coupling constant, the value of T2, the hertz per point in the T1 dimension, and the delta delay. And the result is that you have this kind of optimum value of the delay. This is the ratio between the optimum delay to the matched delay, which is 1/4j. And you see, if you have, and these are the various curves for j by line width. That means if you have sharp lines and lines where it's small compared to j, you are somewhere on this curve. Okay, and if you have taken very crude data set, then you can use you need very large delay, almost as much as dictated by the coupling constant. But as you increase your resolution in the T1 dimension, you need less and less delay. Or as your line width is increasing, you need less and less delay. This gives you the maximum signal for a given delay. How much is the maximum signal for a delay? And so these curves also tell us what we should do in T2 dimension, because there we increase this hertz per point quite a bit, and then we need a smaller delay in T2. So often the optimum experiment is one in which you have a slightly larger delay in T1 and slightly smaller delay in T2. Okay, so so far about these schemes with this kind of delay, which we have called super schemes. There is another set of experiments which have been developed, which are named scaling experiments, in which one of the parameters, either J coupling, either the coupling or the chemical shift, is scaled. The idea is the same, that you're trying to increase the intensity of the cross peak somehow, okay, in the scaling experiments. And the simplest idea is that you increase the value of the apparent J. If you increase the coupling constant, the apparent coupling constant, then these antiphase signals will not cancel. Okay, and so you will get larger cross peak intensity. And therefore the experiment also looks very similar to the super scheme. The experimental scheme for J scaling, J scaled COSY, is again a delay, but here it's not a fixed delay. This delay is incremented with T1, is a function of T1, with a 180-degree pulse in the middle. The 180-degree pulse in the middle of this delay does the following thing. It focuses the chemical shift during this period. So there is no chemical shift increment. Chemical shift is only seen in this period. So there is no chemical shift scaling. But the J coupling is not affected by the 180-degree pulse because it has two I operators in it. And both of them change sign, and therefore J coupling is not affected. And the J coupling is effective during the entire period from here to here. If that is clear, then it is straightforward to see that the chemical shift is not affected, but the J is 1 plus 2k times J. So your J's are pulled in the omega 1 direction. And the result of the experiment looks dramatic. This is the COSY without scaling, and this is the J scale COSY. And the J scale COSY has a lot more intensity compared to COSY. Okay, the intensities are bigger here, you can see that. And you can see the problem with the J scale COSY straight away. Also, that the cross peak of one multiplet, one spin system, is now overlapped with the other even worse, much more. The resolution is decreased here. The intensity is increased, but the separation of the peaks from one spin to another is decreased because you are really spread them out. And so that's no good. And therefore, the idea will be, well, instead of doing J scaling, maybe we should do omega 1 scaling and pull them away. And it might improve things. And so the idea of omega 1 scaling comes in. And the omega 1 scaling has two schemes. I'm not quite clear why one is better than the other, but it's something to do with the way the line widths are scaled in this case. I'm not going to go into the details of the line width scaling, but this is how the scaling experiment works. We have this period here. We actually add then a constant period. A constant period out of which part of it is utilized for chemical shift evolution, and part of it which is not utilized for chemical shift evolution. This pulse is right in the middle of this delta period for the first T1 experiment, and as T1 increases, this 180-degree pulse from the middle, it just goes nearer and nearer and nearer to the 90-degree pulse. That's what's happening. The details are that the chemical shift is effective from here to here. and not in this period. The J coupling is effective over all the time. So the J is effective for T1 plus delta, the chemical shift for T1 plus KT1. But this fixed time period is not Fourier transformed. Okay, so only what is Fourier transformed is the T1. We're doing Fourier transform with respect to T1. This will only add a phase shift. It will not add a frequency. Okay, so J is not scaled, but delta is scaled. And you need a minimum period, minimum delta for this experiment, which is equal to K times T1 max, because of course you have to take the 180-degree pulse all the way from middle to the end. And indeed the experiment works, and this is the experiment with the scale, and you can see that there is more resolution than this, but there is less intensity than this. Okay, the intensity loss is apparent. The second scaling experiment has a slightly different logic. The delta period is not from here to here, but this total period is defined as delta minus T1. Okay. And again, as you can see, the J is not scaled, and delta prime is scaled by the same factor 1 plus K delta. And this experiment has an interesting feature. The feature is that the interval between these two 90-degree pulses, which is the real period in which you're doing coherence transfer, this pulse, interval between this pulse, for the smallest value of T1 is largest. And as you increment T1, the interval between the two 90-degree pulses is decreasing. This is opposite to all the experiments that we have so far thought about. All other experiments were like this. That in the very beginning, the two pulses were very near, and we incremented them, this interval. This experiment has a funny feature that it starts with an experiment like this, and it goes backward. And this is interesting because if you look at the signal that you're going to get here, it is actually increasing with time rather than decreasing with time. And this is what we expect will happen if we had multiplied the signal with an increasing exponential, which amounts to a resolution enhancement filter. Okay, so it has an enhanced resolution in that. And therefore, omega-1 scaling enhances resolution. The sensitivity is decreased because that also is decreased in the experiment in which we have this business of increasing exponential. And this is seen clearly that this is the second scheme of the scale COSY, omega-1 scale COSY, and it has higher resolution than this and lower intensity. Between these two, this looks better. And I think this feature of the increasing intensity makes the resolution better, and therefore this is a better experiment to do. The next scheme in this is the scheme in which it's called scaled COSY simply, in which they have combined both the omega-1 and the J scaling at the same time and give it as a parameter. The very little difference between the two, what they have done is they have multiplied this T1 by a gamma T1, and as you do that, it's easy to see that your chemical shifts are scaled by 1 plus K times delta, and J prime is scaled by gamma J. It's redefining things. Of course, the experiment has similar features, including in the result. You can scale both of them.
Is this a mathematical problem with this growing signal when Fourier transforming is apodizing really?
No, there's no mathematical problem. No. There's no mathematical problem. The only problem would be when you apply a exponentially increasing filter function, is that you should not apply with a time constant which is greater than the line width. If that happens, you get a negative line width. Okay, which means in this case, in this case, you can't think of it this way. Anyway, you have some signal here. So that is not. I guess that will become a contradiction where you must have this minimum values of deltas, otherwise you will get into trouble perhaps. I don't know where will it get into trouble. I haven't done these experiments myself. This is propagated by another group from India at Bombay. Some of these experiments are done by those people. Okay. As you can see very simply that in this scale COSY, if you now make, for example, your gamma as 1, then you got back to the previous scheme. But if you make your gamma equal to 0, what does that mean? That means you still have T1, but you have a fixed delta between these two pulses. Okay, and the J prime would become 0. That means the splitting due to J will disappear. Okay, but you still have your experiment, and that is called omega-1 scaled, omega-1 decoupled COSY. That is, you are decoupling the J coupling in the T1 dimension. And it is exactly the same experiment. What we've done is put gamma equal to 0. So we have